Hello, everyone. The speaker of today is Rattew, who's a visitor at CQT for a few more weeks. And he's gonna present his work in preparing arbitrary continuous function in quantum registers with logarithmic complexity. Thank you, Arthur. You can start.
Yeah, thank you for the introduction, Alessandro. Yeah, and thank you everyone who's attending both in person and remotely. So yeah, as Alessandro said, the purpose of this talk is to prepare, to present the latest work I did in collaboration with the postdoc I did in my group at Oxford. The postdoc is Don Kotzer. He was excellent. We both contributed equally to this work. Normally, I would give this presentation jointly with him, but since it's sort of in person and he's in the UK, that might be a little tricky to do. So yeah, anyway, but it was a pleasure working with him. So the title of the work is Preparing Arbitrary Continuous Functions in Quantum Registers with Logarithmic Complexity. Before I go into the algorithm, I'm just going to present some information motivating the problem of state preparation. Then I'm going to summarize some of the existing work in the space. And then I'll present the algorithm. Okay, so the problem of state preparation is important because there are a range of quantum algorithms that can present or give both polynomial and exponential speedups over their classical counterparts, but only if their inputs can be prepared without introducing any new bottlenecks. In particular, in this work, we're concerned with inputs that correspond to discretized continuous functions. And there are a number of applications that specifically care about these types of inputs. For example, in option pricing and finance, and in real space molecular chemistry simulations. In these applications, you basically want to start, you want to have a quantum register that starts off following some discretized continuous function. Then you want to perform some dynamic simulation on it. And then you want to either get out, so you want to get some output statistics out at the end. Okay, and so there are a couple of existing algorithms that address this problem. The first one was the Grover-Rudolph algorithm, which was presented in like 2001 or 2002. And it requires an efficiently integrable real non-negative function. And iteratively prepares the quantum state according to the integrals in each grid region. So basically in this figure, you can see that the algorithm would start on one qubit. It would assign an amplitude to the zero state that corresponds to the density of the function in the left half of the interval. And same for the one state, it would assign the amplitude corresponding to the density of the function in the right side of the interval. Then coherently in superposition, it determines how much each half of the interval that it splits needs to be increased and decreased so that the relative proportions of the new densities are obtained. And then it recursively repeats this procedure with one oracle call per new qubit added until it gets a good approximation to the function. So this is the asymptotics of this algorithm are similar to the algorithm we present. The main limitation, though, is that it requires quantum integration. And so any applications where you the objective is to perform quantum Monte Carlo simulation or something along those lines, or quantum integration, you obviously lose any speed up by using this technique since you have like an integration algorithm built into it. So this technique works, but not for those problems. And also, yeah, it only works for real non-negative functions. Then there are some other algorithms, such as mixed product state approximations. These require smooth analytic functions. And they work by constructing piecewise polynomial approximations to the state that you want to prepare. So it basically breaks the grid into a number of regions, and in each region it uses a polynomial approximation and it chains them together. So the error in this approximation is fundamentally limited by the use of piecewise polynomial approximations. And moreover, they don't actually present the general bound on the error when you use this procedure. Then there are techniques such as rejection sampling, which have similar asymptotic properties as the algorithm we present in this work, but they're inherently probabilistic. Okay, so now I'm just going to quickly formally state the problem that we're trying to solve, and then I'll state the main result. So we assume that we have a continuous function f on some closed real interval a to b. Then we define a grid with n evenly spaced points on that grid. And then we basically want to prepare a state where the amplitude of each basis state corresponds to the function evaluated at that grid point. So for example, like the grid point x1, you would evaluate the amplitude you would want would be the function evaluated at x1, and then obviously the whole state would be normalized. So the advantage of this is that this pointwise encoding is that it removes the need for quantum integration. And actually, asymptotically in the limit of infinite qubits, their two approaches are equivalent. And in practice, for like Lipschitz continuous functions at least, you exponentially in the number of qubits like suppress the error from this pointwise approximation. But the fact that we don't use the integral in each grid region and that we only evaluate the function actually makes it harder to prepare the state deterministically. So the last assumption that we make is that the function that you want to prepare is efficiently computable. And what we mean by that is given an input, it returns the output with complexity that's polynomial in the number of bits of the input and the number of bits of the output. Intuitively, if there's an efficient classical program computing the output of the function for any given input, then the function is efficiently computable. Like for example, if there's a Python program. And equivalently, efficiently computable means that there exists an oracle that performs the mapping shown here. So basically, it just couples the function value to a state with the input. Okay, so this is the main result. I'll just quickly summarize it. Then I'll explain how we arrived at this result later. And then I'll also define some of the properties stated here, such as the filling ratio. Okay, so basically for an efficiently computable continuous function f, our approach prepares the n-qubit state corresponding to the pointwise encoding with the resolution equal to the number of qubits up to an error epsilon with query complexity given by the filling ratio to the power of -2 divided by the square of the desired error. Here the error is defined as the fidelity, essentially the fidelity of the state relative to the ideal state, or equivalently, in the deviation from the unitary that we implement from the exact ideal unitary, the spectral norm of the difference. The algorithm uses a linear number of ancillary qubits and has a probability of failure bounded by the error squared. Now, a failure probability of epsilon squared might seem strange. There's not many algorithms have a failure probability that decreases as you decrease the error of the procedure. Like normally you would expect if you decrease the error of the procedure, the probability of failing increases because perhaps you're performing more probabilistic steps in a row. And so you'd have some sort of exponential decay in the success probability. But that's not the case here. And sort of the reason for this is that the failure probability that we state here is more of an analytical convenience than it is actually a property of the function. We make this assumption so that we can easily bound the error in the overall procedure. But in practice, so the reason why it's quasi-deterministic depends on how it works, but the gist is that to prepare the state, we perform a sequence of Hamiltonian simulations. And in each Hamiltonian simulation, we measure an ancillary register. And this bound assumes that you only keep a certain outcome of the ancillary measurements. But in practice, you don't actually need to do that. You can keep any outcome that you get, and thus you succeed nearly deterministically. Now, there is actually an exponentially small outcome measurement. So if you accept any measurement outcome, almost all of the outcome measurements have bounded error until the procedure works. But there is, for certain functions, there is a measurement outcome that happens with exponentially small probability that has unbounded error. And so in this exponentially unlikely case, the algorithm can actually fail. So it's not strictly deterministic, but the probability of failure in practice is actually exponentially small. And so in an updated version of the paper, we're going to include this proof of the quasi-deterministic. So we call it quasi-deterministic because in a single run of the algorithm, there is a failure probability that is exponentially small in the desired error. And it's important to stress that this exponential success probability and even the polynomial success probability we have stated here comes from a single run of the algorithm, not from running the algorithm multiple times independently and then selecting whichever outcome succeeds. It's obviously straightforward to get an exponentially high probability of success if you do that, but that's not what we're saying here. Okay, so now I'm just going to motivate the filling ratio. I'll define it formally and then provide some intuition. Basically, the filling ratio is defined as the integral of the absolute function in the interval you are considering. divided by the area of the bounding box, where the bounding box has width equal to your interval and height equal to the absolute max value of the function. So in this figure, the filling ratio is simply the shaded blue area divided by the white area, so like the area of the total bounding box. So it's that divided by that. And as the filling ratio gets smaller for more peaked functions. So when the area under the function gets smaller, anyway, as the function gets more peaked, the filling ratio decreases. And the cost of the algorithm is larger for smaller filling ratios. So the algorithm has a larger constant cost when the function is more peaked. There are a number of tricks you can use to reduce the impact of the filling ratio. Like, for example, if the majority of the function density is contained in a very small percentage or region of the grid, you can just prepare the function on that grid interval. So you define the interval to be just the interval containing most of the density. Then you can add qubits in the zero state to scale up the overall grid to make the grid wider effectively. And then you can just use simple quantum arithmetic to shift the function to the final position that you want. And by doing this, you minimize the cost of the constant cost of the filling ratio. Alternatively, you could use non-uniform grids. And so basically you take more sample points of the function in regions where most of the density is contained. And in doing this, the effective filling ratio is increased, so the cost is decreased. But we leave such non-uniform grids as a topic for future exploration. And finally, the filling ratio is an asymptotic property. As I mentioned, it depends on the integral of the function. But in practice, you're using discrete functions. So it's an asymptotic property, not a discrete quantity. But in practice, you exponentially approach this asymptotic property in the number exponentially in the number of qubits. In our experiments, you converge to it with fewer than 10 qubits usually, and basically in practice, almost always with fewer than 25 qubits. And so this figure illustrates two concepts. One, as the function becomes more peaked, more narrow, the filling ratio, which on the panel on the right corresponds to the dotted gray lines. So for example, the filling ratio for the far right function corresponds to the dotted line on the bottom.
So each of these lines is a function.
Yeah, so each of these lines corresponds to the filling ratio or the generalized filling ratio, which is a concept we'll talk about in a moment, for these functions. So for example, this big wide Gaussian has a filling ratio that corresponds to this line on the top.
Okay.
So basically you can see as the function becomes more peaked, so in this case, as we decrease the variance of the Gaussian, the filling ratio decreases. So yeah, so the filling ratio of this very narrow Gaussian is 10 to the minus 2. Yeah, and anyway, so as you increase the number of qubits, the discrete filling ratio, the generalized filling ratio, asymptotically exponentially approaches the continuous filling ratio that we mentioned a moment ago. And here's some examples of the values of the filling ratio for some common functions with different parameter settings. So generally, basically, you see filling ratio values that range from 0.5 roughly to 10 to the minus 3. So in practice, it's really not that significant of a cost. Here, I'll just briefly mention the generalized filling ratio. So our result was stated in terms of the filling ratio, which, as I mentioned, is an asymptotic property. But you can equivalently state it in terms of the generalized filling ratio that applies for any state you might want to prepare, not just continuous states. And it depends on properties of the discretized function vector. So in particular, given the normalization factor of the desired quantum state, which is essentially the norm of a vector embedding of your function that's unnormalized, and the infinity norm, or the maximum value of the function or of the discretized vector, which we call m, our general result replaces f with f tilde, which is defined as the square of the normalization factor divided by n times the maximum value squared. So for continuous functions, as n approaches infinity, this converges to the filling ratio. But an important detail to note here that may not be immediately obvious is that the square of the norm of your discretized function vector for continuous functions is asymptotically of order of the dimension of the discretized function vector. So to understand this, it might be helpful to consider a specific case. Let's say a uniform distribution. So f of x is equal to 1 for all x. You embed this in a discrete vector. So it's an all one vector. Then the norm of this, the L2 norm, for example, of this vector will just be the sum of all the vector elements. So it's clearly just equal to the dimension of the vector. Now, what about like a less trivial example? So if we consider like a normal distribution, the shape of the distribution is fixed. It's independent of the number of grid points you have. And the values of the function are constants essentially. So as you increase the number of qubits, you're actually summing exponentially more constant values. So basically you're summing a number of values that are of order n. I mean, there's—
Why do you mean wait, constant?
Because the value of the function doesn't depend on n, right? So it's f of x returns some fixed value and it doesn't depend on the resolution of the grid you're using. There's like a simple rigorous argument to prove this, but like I won't bother going into the detail here. But yeah, so this is an important property, and actually the constant factor in front of this asymptotic bound is actually what ends up giving like the integral of the absolute value of the function. So basically, the difference between this asymptotic property and the actual value of the dimension depends on the integral of the function, which is where the in the asymptotic limit, which is where the filling ratio I mentioned earlier comes from. Yeah, so the key is that the function is fixed and independent of the grid. And actually, sorry, just as a quick note, when you present the result in terms of this generalized filling ratio, you can actually use the algorithm to solve unstructured search, but obviously you would expect to not be able to do that efficiently, and it turns out to be the case. In the unstructured search case, the filling ratio is of order, like this term is of order big N, or sorry, big N squared, or the square root of big N. So the actual cost of the algorithm asymptotically is of order N, so it's actually like quadratically worse than just performing unstructured search in the normal way if you were to try performing it just directly via state preparation. It's interesting to note that if you were to improve the dependency on the filling ratio quadratically, then this algorithm actually completely recovers the square root speed up of unstructured search. And so in that sense, it would be optimal in terms of this parameter. But that's like left as a topic for future exploration. Okay. So now I'm going to discuss an important subroutine that enables this state preparation procedure. So basically, given the state that you want to prepare, we define a rank 1 projector onto that state. An important contribution of our work is the ability to efficiently simulate this projector. And this powerful technique is based off of the low rank simulation technique result by Patrick Rebentrost in 2018. And so basically the way this works is we have our function that we want to prepare. We take pointwise samples of it, which go into the entries of a vector. Then we define a projector, which is the outer product of this vector with itself, which gives us the Hamiltonian we want to simulate. And then we perform Hamiltonian simulation according to this projector using the technique, using this technique, which is efficient. So the way this rank 1 simulation subroutine works is you have an H. In practice, you don't know the normalization factor. So you define the matrix elements of the H exactly as the value of the function xj multiplied by the value of the function xk for element hjk. So H is n by n and it's dense. So then we embed H in the n squared by n squared one sparse matrix SH. And this matrix acts on 2n qubits. So rather than acting on 1 qubit, it acts on 2n qubits. And it's one sparse, which is important because it means we can efficiently simulate this matrix with 0 error and with constant cost, independent of t. So you can fast forward the simulation of one sparse matrices. So this is actually a generalized swap matrix. If all the elements of H were equal to 1, then this would just be a swap matrix. And then so we simulate the evolution according to this generalized swap matrix on 2 n-qubit registers. The first register is in some initial state, psi I, that we want to simulate the evolution of that we want to perform simulation with that as the initial state. And then the second register is initially in a uniform superposition. We then perform a Hadamard measurement. Basically, apply a Hadamard measurement to every qubit, or so we apply a Hadamard transform to every qubit in the second register, and then we just measure it on a computational basis. And then the state that's left over in the main register corresponds to the exact simulation we would have wanted of the dense n by n matrix, plus some orthogonal error state. Sorry, this should be psi I there, not plus. Plus some orthogonal error component, and the orthogonal error component, the norm of it can be made arbitrarily small by just increasing the number of discretization steps in your evolution. So I'll talk about this more in a moment. Yeah, so in the theorem that that we stated a few slides ago, the success probability comes from the fact that we only accept the measurement outcomes where we measure all zeros, so corresponding to a plus measurement. But of course, in practice, you don't actually need to do that. But it's very complicated, like the actual details of when, like, what happens when you don't accept, or when you do accept any measurement. So anyway, I won't get into that in this talk. Okay, so now I'll just present, now all the tools required to actually present the algorithm have been presented, and so this is the result. First, we define a time-dependent projector, and we do that by defining an interpolated function for some normalized time parameter between 0 and 1 that interpolates between some easy-to-prepare state, f0, for example, it's the constant function, and a final function that corresponds to the function that you want to prepare. Then for any given s, we define a state which is proportional to the pointwise encoding according to, because this is still a continuous function, right? Because f1 is continuous, f0 is continuous. So the linear combination, convex sum, whatever, is still continuous. So then this state psi s is some intermediate state that we want, that we define, and then we define a time-dependent projector onto this intermediate state. So now we have a time-dependent projector that, if we evolve according, like we can do an adiabatic evolution according to this time-dependent projector, starting with our initial state, that's this uniform superposition, and then we morph it to the final state that we want to prepare. And as we mentioned a moment ago, we can perform the efficient evolution simulation of such a projector, since it corresponds to a projector onto a continuous state. And so this animation visualizes this procedure. So we start with a uniform distribution, and then as s increases, we end up in the final state that we want to prepare. Okay, so as I just mentioned, we do an adiabatic evolution, starting with a uniform superposition. In practice, we can't perform a continuous evolution, like a continuous adiabatic evolution. We have to actually discretize the adiabatic evolution. And so we discretize this time-dependent adiabatic evolution by performing our successive time-independent evolutions. And in each time-independent evolution, we're basically evolving according to the Hamiltonian with s uniformly interpolating between 0 and 1. So if psi is the final state, then this adiabatic evolution produces the state psi plus an error term, and the norm of the error term can be arbitrarily suppressed by increasing r. In particular, we prove a couple of things. One, that the discretization error can be made arbitrarily small efficiently by increasing r. Two, that increasing r also arbitrarily suppresses the simulation error. And then that three, that the total adiabatic evolution time that we need to evolve for is constant bounded. So normally, okay, so basically the way adiabatic evolution works is you start with some initial state, that's the ground state from the initial Hamiltonian. Then if you slowly morph your initial state according to a time-dependent Hamiltonian, if you're morphing slowly enough, you will end up in the ground state of the final Hamiltonian that you end up with. So defining slowly enough is usually what's tricky. And in fact, what you need to do is evolve evolve inversely proportional to the square of the spectral gap of the Hamiltonian. And then there's another factor that depends. If you can bound the spectral gap, then it's usually easy to found the other property. But anyway, effectively, you have to evolve inversely proportional to the spectral gap of the Hamiltonian. In general, it's tricky to prove a lower bound on the spectral gap. But in our case, since our Hamiltonian is a rank 1 projector, its spectral gap is actually just the same as its spectral norm. And so it's easy to lower bound its spectral norm. And so that's how we end up proving that the total evolution time you need to evolve for is constant bounded. Yeah, have I forgotten to say anything here? I think that's everything. Okay, so then we do some full numerical simulations where we simulate and this simulation takes into account all of the error contributions. So we have the Hamiltonian simulation error from like the low rank simulation procedure. We have the function value discretization error, which comes from discretizing the value of the function with d bits. We have the adiabatic evolution error from the adiabatic simulation. And then we also have the adiabatic discretization error all included in the simulation. Okay, so these figures are a bit busy, but basically what's happening is on the left panel, we show the function that we want to prepare, which is the function in black. And we show the adiabatic evolution via the color gradient. So for any fixed color, you'll just get a single function that corresponds to a certain value of s. So for example, s equals 0, it's like the light blue function. That's the uniform superposition. And for s equals 1, it's the black function that corresponds to the final function. In the middle figure, we show the state preparation infidelity as a function of the number of qubits. And I'll say why this is useful or interesting in a moment. And then on the right panel, we show the state preparation infidelity as a function of the number of iterations R you perform. So the resolution and the temporal discretization of your simulation. And so, yeah, okay. So there are a couple interesting asymptotic trends to note here. The first is that as you increase the number of qubits, the error remains constant. So the error is independent of the number of qubits that you prepare the state on. There is a small caveat to that, which is for sufficiently large number of qubits. Because obviously, if you're discretizing a function according to pointwise function evaluations for like a small number of like qubits for a small number of grid points, you might, let's say you have an oscillatory function and you sample the function everywhere where it's 0, then the norm of the vector for a small number of qubits would be 0. So it's like an ill-defined problem in that case. So for a less extreme example, you might just be sampling points that aren't exactly indicative of the actual function. So the error, so you're basically preparing a state that's different than the function. So the actual error might change a bit. But anyway, as you increase the number of qubits, you exponentially approach the exact function that you want. And so basically at a certain point here, it's like 6 qubits for these functions. You basically the error just becomes a constant and independent of the number of qubits. That may have not been 100% clear. So,
What are any colors?
So, oh yeah, okay, so yeah. And the different colors correspond to different values of R. So as you go from like black to red, you are performing more iterations R. So here, and in the panel on the right, so for example, for black, you're doing something like 10 to the 4.5 iterations, and you get an error of 10 to the minus 4.5. Similarly for red, and so on and so on. So this is showing that as you increase the number of iterations R, you arbitrarily suppress the error. Yeah.
There's a question from the audience. Why is the infidelity increasing for the second function in the asymptotic limit?
Yeah, so basically, it could be the case that the specific discretization. So for example, for 1 qubit, the discretization you have, basically it's not the function that you're preparing, it's like some discrete function that's arbitrary based off where you take the samples. So if you shift the samples that you take slightly, then the error could be different. So it just depends specifically on where you're sampling the function for a small number of samples. But as you increase the number of samples, it becomes independent of like the specific location you sample because you're taking a dense enough selection of samples. And since the cost of our algorithm is independent of the number of qubits, there's like no reason really why you wouldn't just run this on 128 qubits, where you could resolve the Planck scale on a grid of 1 kilometer. So like in practice, this is just not a problem. Yeah. But yeah, thank you. That's a good question. That is an interesting feature. And actually, we forgot to mention that in the paper, so we're going to add that to an updated version of the paper, just a note on that topic. And also these numerical simulations show that our error bounds are actually quite loose, because our error bounds show that the error should decrease as the square root of 1 over r. But in practice, we're seeing actually it's 1 over superlinear in r. So our error bounds are very loose, and like for example, for 10 to the 6 iterations, you're getting roughly an error of like 10 to the 6.5 iterations, you're getting roughly an error of 10 to the minus 7. So yeah. Okay. So now we've basically talked about most of the important properties, at least at a high level. Yeah.
Do you observe per bound of the state in which your error diminishes with r? You get like 1.3, 1.19.
Are you saying like you get like diminishing returns? Like this isn't just linear. If you keep increasing r, it'll like plateau. Is that what you're asking?
No, I mean to find out other functions for which the rate is even faster.
Maybe you can repeat the question so people online can hear.
Oh yeah, sure. So the question was basically, are there different functions for which the convergence rate in terms of r is even better, or perhaps even worse than the functions we've shown here? Possibly, yeah. I mean, certainly it cannot be worse than the lower bound, than the upper bound in terms of the convergence that we proved. So like it's guaranteed. The worst that it could possibly be is square root of so basically r to the minus 1/2. But whether it can be better than these values is a good point, and we haven't really thought about that much. And it'd be interesting to see. Let me think for a moment. If I can think off the top of my head of a function for it.
1.3 is much better than half.
Yeah, no, absolutely.
Like,
yeah.
Could it get even better, like 1.5? I mean, you haven't seen that on minus.
To be honest, other than the 2 examples we ran here, I didn't really pay attention We didn't really pay attention to what the specific powers were. But no, that's interesting.
There's another question, like, could you find examples in which is very close to
the lower bound?
So
yeah, so I suspect that the lower bound that you would find is actually inversely linear in R, because the square root comes from the adiabatic error, and the bounds in the adiabatic, basically from the adiabatic discretization error is where the square root comes from. And that's like a very, very loose bound. And so there are more sophisticated techniques that could give you tighter adiabatic error bounds. And when you do that, I think you'd end up with something that basically the dominant error comes from the simulation error, which is inversely linear in R, rather than the adiabatic error. So I do think you could tighten it to get a lower bound of 1 over R. Yeah. But in what cases it's better than 1 over R, we haven't really thought about much. Yeah, that is interesting though. I feel like there might be, anyway, I won't speculate live in the presentation. Yeah, okay, anyway, so that's basically all I'm going to talk about the state preparation procedure. Now I'm just going to talk about some of the potential other applications that are enabled by this low rank simulation procedure. So given there's Hamiltonian, which is a projector onto some state, and the ability to simulate it, there are some interesting things you can potentially do. So one is the integration of Lipschitz continuous functions. So just before I go into this, it's worth noting that this has similar asymptotic performance to existing quantum algorithms. And the error scales is something like 1 over epsilon, like in principle. We haven't comprehensively done the error analysis in this case. But yeah, so the error scales is something like 1 over epsilon. The interesting part of this approach is that it could potentially lead to a way to polynomially improve the error dependence in the integration error over the existing quantum integration techniques. But basically, anyway, the way it works is that you have a projector that's proportional to a projector onto the state you want to prepare. But precisely, actually, what it's defined as this, where phi is your unnormalized quantum state that you want to prepare. And the eigenvalue of this projector onto the state psi, which would be the normalized equivalent, is simply equal to the square. So actually, I think this phi here should be a psi. But anyway, the eigenvalue that you care about is equal to the normalization factor squared divided by n, and all other eigenvalues are 0. So if you do phase estimation of this quantity and you read out the value 0 in your ancillary register for the phase estimation, you've read out one of the degenerate eigenvalues, so you don't care, so you try again. But if you read out a non-zero eigenvalue, then what you've actually read is equal to t times normalization factor squared divided by n. And since you know t and you know n, you can then compute the normalization factor squared, which for Lipschitz continuous functions basically immediately allows you to determine the integral of the function with exponentially small error in big N, or sorry, in the number of qubits.
And you do phase estimation on which initial state?
So it depends. If it depends. If you can actually just prepare the state, then you can just do it with that, and then you don't even have to worry about the success probability. But if you can't, you can just do it with the uniform superposition. And technically, the overlap of any continuous function with the uniform superposition is a constant that's independent.
Ah, nice.
Yeah, and actually, the constant ends up basically being something depending on the filling ratio and like the width of the interval. So the probability of success then depends on the filling ratio in that case. Yeah. There was something I wanted to say. Anyway, so this procedure as stated works basically for non-negative real functions, but you can easily generalize it to arbitrary complex functions, like by just splitting the complex function into 4 quadrants, where you have all the positive real parts, all the negative real parts, all the positive complex parts, and all the negative complex parts as separate functions just on the real plane. Then you can compute the integral of each of those functions and then just add them together, and that gives you the integral of the overall thing. So you can do that with the normalization factor. Yeah, okay. And then the last application that I'll potentially mention, potential application that I'll mention, is in the global optimization of continuous functions. So basically, if you want to if you want to optimize the function f, rather than preparing the state corresponding to f, you can prepare the state corresponding to g of x, which is defined as f raised to the power of k. And obviously, as you increase k, the probability, and you prepare the state, the probability of measuring the global maximum value increases exponentially in k. Because if it's greater than 1, if the maximum is greater than 1, then this will be exponentially increased faster than any other values. It's the maximum. And if it's smaller than 1, all the other values will be suppressed faster than it is. The only problem is you increase k, you're also exponentially decreasing the filling ratio. So the oracle complexity of preparing the state increases. But for certain functions, it might actually be the case that the rate at which the the query complexity increases is less than the rate at which the maximum value of the function is increased. And so it might be interesting to see for what families of functions this could actually be a potentially useful global optimization technique. And then finally, I'd like to give a special thanks to the JP Morgan Chase Future Lab for Applied Research and Engineering for numerous helpful and insightful conversations. I did do part of this work while I was at JP Morgan as an intern last summer. Yeah, so just like to acknowledge them. And then there are also a ton of other people who helped, like my advisor at Oxford, Simon Benjamin, and then various people who gave helpful like comments on the proofs, like Dylan Herman at JP Morgan and US Sun at JP Morgan. And then also Patrick gave some thoughts. So thanks to everyone. Yeah, thank you. Any questions?
So thanks for the talk. If anyone in the audience has questions, maybe or remotely, otherwise, maybe I have a few questions. If you can please re-explain again, like R is function of the precision that you want.
Yeah. And
capital T.
Yeah, and capital T and the filling ratio.
And the filling ratio.
But I mean, capital T is constant bounded. But yeah.
And also, so here you assume that you have query access to the function. And this capital M is basically the L infinity norm of the function.
Yeah, squared. Or,
Square.
sorry, yeah, M is the L infinity norm of the function. It's not.
Okay.
Yeah.
And but if you have a circuit that gives you query access to F, with a circuit for and you know the L infinity norm in advance, you can also build query access to the function F divided by the M. And I guess that the two states that you can prepare are equivalent because one is just so you can eventually remove that factor from the runtime. No?
What would happen though is that would end up changing the norm of the discretized function because you've rescaled it by n. So I think it would end up popping back in implicitly through the norm of the discretized vector. What slide is it on here?
At the beginning,
so,
exactly.
So n squared. In this case, if you divided the function, all the function values by n, then your norm of the function would have 1 over n, and then the norm squared would be 1 over n squared, and then so you could factor it out, and then you'd end up back here.
Too easy.
But yeah, nice.
I tried.
Nice try. Yeah, in practice, you don't actually need to know the value of n. You just need to be able to like upper bound it. It doesn't impact your success probability, just like the value of r you need to select. So if you can just like overbound it, like even by like 2 orders of magnitude, it still works. Just makes your runtime 2 orders of magnitude slower.
So it's a diabatic, not because you're doing adiabatic computing, but because in the circuit model you are doing a Hamiltonian simulation of a function that is slowly changing.
Yeah, we're discretizing the adiabatic.
Okay. Yeah. So it's
so it's in a circuit model.
Exactly. Cool.
Sorry, you had a question?
Yeah, just to clarify. So you assume you have access to the function F.
Yeah.
And what you require is that you wish to you have to design the Hamiltonian with F as the input. So there is, your experimentalist, or you input the function F into the computer and it designs that Hamiltonian and executes that Hamiltonian.
Yeah, exactly.
But that means that you need to know how to create the state file.
What do you mean?
Because for the Hamiltonian if you wish Hamiltonian to be the projector file, you will need to somehow know how to do that file, correct?
No, I maybe.
Can you repeat the question for the audience?
Oh yes. Sorry, I think I'm not understanding the question yet. So sorry, could you?
Sure. I'm not very familiar with this, so maybe I'm asking something stupid, but so my understanding is that using the function f, which you know and you can control.
Yeah.
You want to design the Hamiltonian such that it's the projector of the state file.
So you define the Hamiltonian so that it's proportional to the projector onto the state phi. So what it actually is some matrix where the element, let's say jk, is equal to the function evaluated at the jth grid point multiplied by the function evaluated at the kth grid point. So if you have oracle access to the function f, then you just need to make 2 oracle calls to compute the value of that matrix element. And you can do the low rank simulation just using oracle access to the elements of the Hamiltonian. So you don't need to prepare the state to do that.
Right. So, okay. So I'm imagining you have another ancillary of the same dimension, and you kind of use oracle to make the system have that Hamiltonian.
So you don't make the system have that Hamiltonian so much as you implement Hamiltonian simulation. Like if this is all in a discretized model, so you end up producing a specific quantum circuit that corresponds to the simulation of that Hamiltonian for a given value like s. So for a specific time, or actually even in a simple case, you're just evolving according to a single function f. You can construct, there's a procedure that given an efficiently computable function f, that constructs a quantum circuit that corresponds to the simulation according to that function f. Yeah. Yeah. Thank you for the question. Sorry if I didn't.
No, I think it's based on the result that you can simulate this.
Yeah.
Given
yeah. It's built off of Patrick Rebbentrost's 2018 low rank simulation. Thank you for the question. Yeah. Any other questions?
Have you tried to propagate the cost of this technique for state preparation into any other algorithm for, I don't know, Monte Carlo or whatever, to see the final runtime?
Not the only algorithm we've tried to propagate this technique into is for integration of functions. So where the existing classical quantum algorithms are basically like the quantum Monte Carlo algorithms. And we get basically the same error dependence in its current form without any changes to the Hamiltonian simulation technique. We get the same error dependence of 1 over epsilon. So quadratic improvements in the error dependence over classical quantum Monte Carlo. But just based off the fact that our dependence on the filling ratio is squared rather than to the -2 rather than to the -1, we get a quadratically worse error dependence. Sorry, not error dependence. We get a quadratically worse dependence on what is effectively the filling ratio when compared to existing quantum algorithms. So improving that if we made the dependence on the filling ratio linear, then we would have the exact same performance and integration as existing quantum Monte Carlo algorithms. The important part is the error dependence, really, and that's already the same. Yeah, but the hope here is that there might be a path towards improving the error dependence further. Yeah.
Thank you.
Yeah, thank you for all the questions.
I don't know.
Anything else? Any online?
I don't know if anyone has other questions from Zoom.
Okay, in that case, let's see, once I start the chat. Okay, yeah. Okay, cool. In that case, thank you everyone for coming. Appreciate it. Hope you enjoyed it.
Thank you.